skip it.
Okay.
Too.
Well, let's see how good you are with these. Let me get so I can write, take a screenshot. Weird. Not letting me take a screenshot. That's pretty weird.
Not on like window key, like and F12 or whatever.
Windows, here it goes. In other words, if I click that thing, it'll let me take a screenshot, and then I can write on the paper. So the domain for the argument of all log functions has to be greater than 0, not greater than or equal to, but greater than 0. So I'm going to write 4 minus 3x, that's the argument, has to be greater than 0. Solve that, you'll have the domain. So how do you solve this inequality?
You add or you subtract 4 to both sides, or you said equal to 0?
No,
right?
No, you gotta, in other words, because it's a log function, the argument has to be greater than 0. It's kind of like the square root of x. X would have to be greater than or equal to 0. With a log function, it has to be greater than 0. Can't even be equal to it. Okay? So now we got this. Now what's the next step?
X has to, so you divide it by -3.
Okay, and what's that force you to do with the inequality sign?
Switch it.
Okay, so we got x is less than positive 4/3. Now, put that in interval notation, which all of 5 answers are in interval notation. If x has to be less than 4/3, what is the allowable interval?
Should be
Here, let's
0.
Let's do it this way. I'm going to put a number line up there. There's 4/3. X has to be less
than 4/3, but greater than 0. Or
doesn't have to be greater than 0. What was in the argument has to be greater than 0. X doesn't. You're going to see that x can be any big negative number. In other words, it's going to go from -infinity to 4/3.
So it can
That's
be.
what that means. When I say x is less than 4/3, yeah, it could be -10. Notice what happens if I make it a -10. You get 4 minus a -30. That turns positive. So that becomes 40 or 34. I can take the log of 34. So the more negative x goes, the more positive that whole thing becomes. But if you go over 4/3, let's make x 2. Now 4 minus 6 is a negative number. So what x can't be is greater than 4/3 or equal to 4/3. It has to be less than 4/3. And the answer is right there. And it's parentheses as opposed to brackets. Notice this answer over here. What's the difference between a bracket and a parenthesis?
The brackets, it would be like if it's equal to.
Right. In other words, the bracket indicates that it could be equal to 4/3. But in this case, not only do they have it backwards, but they have a bracket instead of a parenthesis. And I know it has to be a parentheses. I cannot have 4/3. If I have 4/3, then it's 4 minus 4. 0 is the argument. You cannot take the log of 0. Okay. Let's go down. Oh, I gotta scroll out in order to scroll down. And then take another picture. Find the range.
So the range would be when x is equal to 0, right?
Well, let's graph a normal looking log function. In other words, that would be y equal natural log of x. What's the range of that function?
Like 0 to infinity.
Remember, the ranges look vertically. When you're thinking,
it's vertically.
You look horizontally. When you're thinking range, you look vertically. In other words, if I'm looking horizontally, I can see that x has to be greater than 0. There's no way not only does it does not touch the y-axis, so x never gets to 0. But y, on the other hand, goes all the way to negative infinity. And it goes all the way to positive infinity. So the range on log functions is generally negative infinity to positive infinity. And it doesn't matter. Well, hold on. Let's give that a second thought. It doesn't generally matter what the argument is.
All right.
Now hold on a second here, though. R is going to be limited, but that's okay. And this point right here is 1, 0 always. And what that means is that when you take the logs of numbers between 0 and 1, you get negative answers. When you take the logs of numbers greater than 1, you get positive answers. So the fact that my argument is 100 minus 3r really doesn't matter. It restricts r to being no greater than 33.
So it'd be b then?
No. Let's see. In log of x, x can be anywhere from 0 to infinity, which means y can go from negative infinity to positive infinity. But in our problem, this has to be greater than 0, which means r has to be less than 33 1/3, or 100/3. When r is close to 100/3, we can go all the way to negative infinity, as long as we don't reach 100/3. And when r gets close to 100/3, yeah, we're at negative infinity, and when r goes negative, we're at positive infinity, so it is e. it does not really matter what that argument is or how R is restricted. In other words, X is restricted up there also. X has to be greater than 0. But the range is still negative infinity to positive infinity. So the range on most all log functions is going to be negative infinity to positive infinity. The only difference here is that it would be translated. In other words, I have a translation of 100 to the left, and I have a reflection. Nonetheless, it could look like that. It's still going from negative infinity to positive infinity. So the argument doesn't really matter. The domain of a log function, you set the argument greater than 0 and solve. The range of a log function, negative infinity to positive infinity. I'm not sure I've ever seen one that didn't have that range. It's difficult to imagine what the argument could be so that the range wouldn't be negative infinity to positive infinity.
Okay.
R were 33, I'd be taking the log of 1, which is 0, so it definitely can be 0. So it's not C. C excludes 0. All right, let's scroll down and look at the next one here. When you solve for the x-intercept, how do you do it?
You set y equal to 0?
Correct. So 0 equals natural log of x minus k plus 2. How do I solve that?
You subtract 2 from both sides.
Okay. Now here's the tricky part. How do you solve that? Still trying to solve for what the 0 is. It's probably
Well, can't you?
in terms of k, as all of our answers are in terms of k. But when you're trying to solve a log function, exponentiate it. In other words, if I put an e under the minus 2 and an e under that, notice what that becomes. What does that
Just
become?
x minus h.
X minus k.
Or yeah, k, not h.
Okay, and that's why we do it that way. This becomes e to the minus 2. So x becomes e to the minus 2 plus k. That is the x-intercept. So when I look for the x-intercept, it's going to be that comma 0. Right there. Is there anything about that solution you don't understand?
No.
Okay. Because there's other ways to do it. In other words, when I was down to this step here, when I had minus 2 equals natural log of x minus k, when I was there, I didn't necessarily have to exponentiate both sides. I could just convert it to exponential format. Well, exponential format is the base to that power equals the argument. So automatically, if I convert this to exponential format, it's e to the minus 2 equals x minus k. So I can get to that step without this fancy maneuver of sticking an e under it. Because all I got to do is know how to convert from log to exponential and back and forth. Do you know how to do that
Yeah.
positively? Because I can give you some to find out.
Yeah.
That's
I'd like just getting it from log to
okay.
you just multiply. I
We
think you
got the
multiply
answer.
by
We
10.
got the answer to 3. Let me just quiz you a little bit on converting from logs to exponential and back the other way.
Okay.
I got to think of some problems. Put that in exponential format. In other words, you always want to go, if it's a log format, you're going to want to do exponential format. If it's in exponential format, you're going to want to do log format. So we just need to make sure you can go both ways. How would I write this in exponential format? Here's the
It'd be
way I remember it. This works well for me. Take the number on the far left to the exponent of whatever's on the far right. Remember, logs are exponents, and it's equal to what's in the middle. So 7 to the x equals 49. Now you can solve it. What does x have to be?
2.
In other words, sometimes you don't need a calculator to solve these. If you can get them in exponential format, the solution becomes almost self-evident. Okay, let me give you another one. Put that in exponential format. What's the number on the far left?
10
Raised to what?
to the x
Equals,
equals 100.
and x again is 2. In other words, by putting in an exponential format, we're able to solve it easily, even though that 10 is hidden. Okay, now let me just give you one going the other way. There's exponential format, and clearly we don't know how to solve that algebraically, right? Even with your calculator, without logs, you would not be able to solve that. X is not 2 and it's not 3, it's somewhere between 2 and 3. And exactly where it's at, the only way we can figure it out, put it in logarithmic format. So, if to put it in logarithmic format, you merely need to remember that logs are exponents. So that much has to be true. Now the only thing you need to fill in is what's the base and what's the argument. What's the base?
It'd be log base 4.
Which leaves the argument. The only thing left is 17. So that is the logarithmic expression of that exponential equation. And now I can solve it because I can get that number out of my calculator. What kind of, you used to have your Inspire, right?
Yeah, I still do.
Well, the Inspire actually allows you to figure out the logs regardless of the base. You can put in log base 4 of 17. The old TI-84 didn't let you do it. You had to use the change of base formula. But as long as we're talking about it, let's go through it because I would imagine that at some point you're going to need to use the change of base formula. Change of base formula is the log of the upper number divided by the log of the lower number. Simple as that. And you can use any log you want. I could use natural log, I could use common log, I could use log base 11 if I wanted. These ratios are all the same, which is another interesting feature of logs. That is the same ratio as the common log ratio. So it doesn't matter when you use change of base. Now, if I had an older calculator, this would be a lot better because the older calculators only had a common log key and a natural log key. They couldn't do log base 4 without using change of base formula. But you can, but I wouldn't doubt that you'll come across the need for the change of base formula. Just they'll figure out a way that you have to know it by using variables or something. Okay, let's scroll down to 4. Simplify the expression. Are all your tests multiple choice? Is that?
Part of them are, part of them aren't.
Okay.
And I believe later in the review it gets to the other answer, like examples of short answers.
Okay. This looks a little tricky, but notice one thing. If I said 5 to the a plus b power, that is the same thing as 5 to the a times 5 to the b, correct? In other words, if I'm multiplying the same base, I'm adding the exponents. That ends up being 5 to the a plus b. So here they're giving you this, and they want you to take it apart into that and that. Okay?
All right.
So let's do that. So what is that expression going to be equal to?
5 to the 2, and then 5 to the log.
Times. And the times is important because we're looking at a plus sign there. But you're right, it's the rest of it. And now that's quite helpful because this is something, what's that equal to?
X to the 5th.
Just x. In other words, yeah, when you have b,
oh yeah, because it's base 5.
Log base b of x, that's always x. If it's of x squared, then it's x squared. It's whatever that is. Okay? So
yep.
That becomes x, that becomes 25, so our answer is 25x. Okay?
Okay.
I'm going to assume if you don't ask something that you understand it, and it's okay to go to the next one.
Yeah.
Okay. Express as a single log and simplify if possible. Okay, do you know the 3 log rules, the main 3 log rules? They're being, I'll write them on here once, but I really want you to memorize them. Equals what? What's the log of a times b equal to?
I do not know. Or log of a plus log of b.
There you go. That's rule number 1. Must memorize these. Not only do you have to memorize them, you got to be able to go both ways. They're going to give you just as many problems where you got to go from right to left as from left to right. Here's rule number 2. What do you suppose that is?
Log of A minus log of B.
And finally, rule number 3, which is kind of the hardest one. If I have the log of A to the B power, what does that equal to?
Log of...
No, this is where you take the exponent and you put it down in front of the log so that it goes on the algebra line. It's no longer an exponent. It becomes log A.
So B log of A. Okay.
Yeah, sorry. I meant that as maybe a way to memorize it, but it's not a bad way to memorize it. Blog.
Blaga.
Yeah, blaga. Yeah. So anyway, these are the 3 rules that you're going to have to use on all these problems like 5, or problems where they give you a single log expression and they ask you to expand it. You're either compressing or expanding. Okay? In this case, we're compressing. We've got 3 log expressions. They want it as a single one. Now, when you compress, you kind of do step 3 first, if at all possible. So if I do step 3 first, what happens to what I have circled? What do I get? I'm going to write it here in the upper left. In other words, do the backwards of blaga. Take the b and make it the exponent of the argument.
So log x of 1/3.
There you go.
Plus log y to the 4th. Minus 2, or wait, no, would it be minus 2 log, or no? Would you bring that minus sign?
Either one would actually be correct. I could put a plus there and a minus there, or I could just make it subtraction. I prefer subtraction myself with the positive exponent.
Okay.
Okay. Now we want to apply rules 1 and 2. Going backwards. In other words, those are being added. So in the argument of my final expression, those 2 things are being multiplied, those 2 arguments. So the numerator becomes x to the 1/3 times y to the 4th. There is a denominator because that is being subtracted. Notice rule 2. When it's being subtracted, you divide. So we want to divide everything by z squared. And that's our answer. Let's see. I've covered everything up. I'm going to have to erase some of this stuff to see whether they've got that.
Yeah, I think it's B. Or no,
I think it's D.
Yeah, it's D.
Yeah, that's D. X to the 1/3, y to the 4th, z squared. What's x to the 1/3 mean?
X to the square root of 3, or the cube root.
Cube root of x. That's what it means. It means cube root of x. Okay. All right, shall we go on? Remember these 3 log rules. They're the same rules for exponents, if you notice. When you are multiplying same base with different exponents, you add the exponents. When you are dividing same base with different exponents, you subtract the exponents. And that makes sense because what I said logs are exponents. But that's an exponent. So is that. So logs follow the same rules as the rules for exponents. All right, I'm going to erase them, but for sure put that on your memory list. Let me suggest something, Zach. If you're having a hard time memorizing some of this stuff, I know the best possible way to memorize stuff.
Yeah.
I probably have told you before.
Practice problems.
Get yourself some 3x5 index cards. And on one side of the index card, put the name of the rule. On the other side, put the rule. In other words, for our 3 log rules, you'd have an index card. On one side, it would say the log of A times B. On the other side, it would say the log of A plus the log of B. So get 3 index cards for those 3 things, and index cards for everything else that you need to memorize. Like if you wanted to memorize that the log base B of B, I'd put that on one card. On the other side of the card, it's always 1, no matter what B is. In other words, the log base 17 of 17 is 1, because 17 to the 1 power is 17. But once you end up with a series of index cards, for one thing, half the battle is done, because you didn't buy these index cards from somebody else. You didn't borrow them from somebody else. You created them yourself. And in the mere act of creating them, you memorize half of the memory problem is taken care of. But then the thing to do to use them, say you got 10 index cards, just shuffle them up, turn them inside out, and make sure that whatever you see on one side of the card, you know what the other side says. In other words, flashcards. And trust me that you won't have to practice very much before you'll have it all memorized. Every single thing that's on every one of your index cards. Every time you come across a problem where you have to memorize something that you do not have memorized, make an index card for it. Guarantee you that will work. Memory is a huge part of math, as you found out with calculus. Calculus was just tons and tons of stuff you had to memorize. All those derivatives of trig functions and integrals of trig functions, and unbelievable. But all math has lots of stuff you need to memorize.
Okay, I have written down here to make 3x5 note cards of the log rules.
Good. And any other thing that you find you have not memorized that you need to memorize. I mean, I'd be happy to point it out, but I'm sure you probably know, right? I mean, at least I think you would know. Maybe not. Like that previous problem, you might not have known that there were 3 log rules that you could apply, and you had to. So you needed to know that that depended on 3 log rules that you had to have memorized. All right. H of t is 5 plus 2e to the t, and they want to find the inverse of h evaluated at 9. All right, let's talk about how we find inverses. First of all, I'm going to change that h of t to y, just because we're used to working with y. What is the process for finding inverses?
Put them over 1.
No, that's reciprocal. In fact, that's what answer E did. is it put it over 1 and evaluated it at 9. Now, this is a subtle distinction, actually. Why that's not the reciprocal. Because if I said to you, what is 2 to the minus 1, that's the reciprocal, I do that. If I say 2 to the minus 3, I do this. Okay? But when I make a function and I put a minus 1 like that, that does not mean reciprocal, it means inverse.
Okay.
Okay, and they are different. The inverse does not mean the reciprocal. Here's how you solve for inverse. Switch the variables and solve for y. It's a two-step process. That's all you do. Switch the variables and solve for y. With me?
Yeah. Why'd you switch the variables?
That's the first step of solving for the inverse.
Oh, okay.
And then solving for y is the tough part. This is not a terrifically easy solution, although it's not that tough. If I want to solve for y, I want to isolate that and then take the natural log of both sides. Because if I take the natural log of that, it turns into minus y. Okay? So, first of all, I got to get rid of the 5 and the 2. How do I do that?
You subtract 5 and then divide by 2.
That's going to be equal to e to the minus y. Now, I'm going to take the natural log of both sides. And when I take the natural log of the right side, this is the same as log base b of b to the minus y, right? In other words, natural log is base e. So the e's are the same, so this whole thing becomes minus y. Okay? So divide both sides by 1, put the minus sign over there. That's what y is equal to, or h inverse of t. So if I want, I can call it h instead of y. I will call it h inverse as a function of t, and it's equal to minus the natural log of the argument t minus 5 over 2. They want us to evaluate it at 9, right? So if I want h inverse of 9, then I plug in 9 for t. Well, now that is a number. I'm going to write it over here on the left. I got minus natural log. 9 minus 5 is 4, divided by 2 is 2. Now, is that one of the answers? Yes, it is, C. Now, the reason I said is that one of the answers is because there's a couple of ways I could write this. Notice that that is a minus 1, right? Which means I can move it to an exponent. So what I have written is the same as this. And 2 to the minus 1 is the same as that. So that is the same as that is the same as that. So they could have had an answer on there, the log of 1/2, which is the same as minus the log of 2, or natural.
So which method would you think I should use on a test?
It's going to depend. If it's multiple choice, you won't have any choice. You'll have to find the answer that is equal to one of these, like I did. If it's fill in the blank, I don't think it'll matter. You won't lose points with any of those three answers. They're all the same number. And just a little tip about logs. If you take the log of a number greater than 1, you get a positive answer. If you take the log of a number between 0 and 1, you get a negative number for an answer. Well, 1/2 is between 0 and 1. So this is going to give us a negative number. But so will this one up here. That was minus the log of 2. Well, the log of 2 gives us a positive number, but then the negative sign makes it negative. But that's a useful thing to remember, is that the logs of numbers, no matter what the base, the logs of numbers greater than 1 are positive. The logs of numbers between 0 and 1 are negative, and that's why the log chart looks like this. Notice that is 1, 0. So anytime x is to the right of 1, we're in positive territory. Anytime x is between 0 and 1, we are in negative territory. If you take the log of a really, really tiny number, 0.00001, you're going to be approaching negative infinity. In other words, the closer and closer I get to 0, the further down that goes. The closer and closer it gets to 0. All right, let's see. Yeah, that kind of notation has bothered me for a long time, because that -1 doesn't mean the same as most -1s mean. It's a little bit like inverse sine, if you think about it. Inverse sine of x does not mean 1 over sine x. It means it's the inverse of sine x function. So it's not the only place where -1 means inverse. Whenever it is part of function notation, like h of x or sine of x or tangent of x, and there's a -1 in there, that means inverse, not reciprocal. You have numbers or letters. If I just said x to the -1, then that's 1 over x. That is reciprocal. But if I have function notation, if I have f to the -1 of x, that does not mean reciprocal. Confusing, I see. Okay, let me scroll down again here. How many total problems are on this PDF?
A lot.
Just like,
I don't know how much are actually going to be on the test.
Just like
because his tests aren't that long.
Yeah. The test is tomorrow?
Yeah.
Okay.
His tests aren't usually super long, so.
All right. Well, I don't know how to do anything here but go through them one at a time. It's not like they're each like the one before it. They're each different. So you kind of have to do them separately. I mean, this isn't really like any of the others. First thing we should notice on this problem is that k is in the exponent. And we're trying to solve for k. When you have an exponential equation, you have to use logs. Okay? So I'm going to have to use logs. And I'd like to take the logs of both sides, which means I'd like to move one of those to the other side. Let's do it. Let's take, hold on. Let's say 5e to the minus 2k is equal to minus 3k e to the minus 2k.
So you have to put it to the natural log of 2k.
Actually not in this case. Why is that? I have an e to the minus 2k on the left, and I have an e to the minus 2k on the right.
You can just divide by e to the minus 2k.
You got it. In other words, this is a very unique problem. We don't have to use logs to solve it because our exponentials disappear when we do that. And so what I end up with is this. Now it's an algebraic equation, not an exponential one. K equals minus 5/3 only. Now, is it really only? What if k is 0?
Well, it can't be 0 because then you'd still have 5e to the minus.
Right,
Like,
you're right.
2.
In other words, you would have 5 times 1 equals 0, and it doesn't. So k cannot be 0. Yeah, in other words, I'm trying to figure out the fact that I divided both sides. You got to be a little careful. Let's talk about this. This is a subtle point, but when you're solving an equation and you're dividing both sides by something that might be 0, you made a big mistake. You don't want to do it like that. In fact, the only reason I was able to do it here was because there's no way that e to the minus 2k can be 0. There is no k that makes that entity 0. E is a number, 2.71. If I take a number to an exponent, positive or negative, it's never 0. So in this case, I was safe doing it that way. Let me show you the way I really should have done it. I should have started with that and factored out an e to the minus 2k. Instead of moving it to the other side, I should have done this. Same thing, right? Only now I know that either that has to be 0 or that has to be 0. This thing cannot be 0. It's impossible for that to be 0. So this thing has to be 0. And if that's 0, you get k equal minus 5/3, and that is the only solution. And that's really the way to solve it, is by factoring out rather than moving it to the other side and dividing. It worked in this case because e to the minus 2k can't be 0. But if it could be, I wouldn't be able to do it the first way. I would lose a solution, the solution being 0. If you divide by something and it is 0, and 0 was a solution, you'll lose it. It'll just disappear. You will not see it. Do you know what fog means?
Yeah, f of g.
Yeah, it's the same as f of g of t. In other words, it can be written like this also. In
F
fact, I
parentheses
kind
g
of
parentheses
prefer it
g.
to be written like this, because then the problem becomes easy. Simplify fog completely. Well, what's the next thing I want to write? If I write it like this, then what's the next thing I want to write?
3 to t.
That's g of t, right? And now, if f is equal to that, what is f of 3 to the t equal to? How do I solve?
Log.
Okay.
Log base 3.
Log base 3.
27.
No, not yet. It's 9 times
3t. Or 3 to the t.
3 to the t, which is not the same as 27 to the t.
And then plus 4.
However, 9 can be written as 3 squared, right?
Yeah.
And this is a neat little trick because I'm looking at all of these 3's.
Wouldn't it just be 2 plus t in the exponent?
What's that?
Wouldn't it just be 2 plus t in the exponent?
Yeah, so now this becomes log base 3 of 3 to the 2 plus t plus 4. And now what does that whole thing become?
Just 2t, or 2 plus t.
2 plus t plus 4, that's t plus 6. E. Okay? See how I got t plus 6?
Yeah.
Okay. But this, to me, is a crucial part, is to write it like that, and then that's also a crucial part. Write it like that. Once you've written it like this, then all you do is go to the f function, and whatever is in the parentheses, stick in wherever you see t, which is exactly what we did. And then we got that, and then we just had to simplify it. Now, simplifying it was no mean feat. I wouldn't have been able to simplify that if 9 had not been a power of 3. In other words, turn that 9 to an 8, and all of a sudden this becomes much more difficult. Although not really, it just occurred to me. You can separate the argument. Look what happens here. I could do it if it was an 8. I don't need to use that nice little trick that I just used. Here, let's do it the other way also. I'm multiplying in the argument, right?
Yep.
So that becomes log base 3 of 9 plus log base 3 of 3 to the t. In other words, I merely separate it, plus 4. Okay? Now that is 2. Right? 3 squared is equal to 9. That is t, and that is 4. And that still gives me t plus 6. Without anything fancy like having to break the 9 up into 3 squared. Just by separating it into 2 log statements solves the problem.
So if log 3, then to log 3, 9 there.
That's the number 2. Log 3 of 9 is equal to 2.
If it didn't go, like, if there was a number that didn't equal a perfect number, you could just write log 3 8 plus
Yes.
t plus 4,
Yes.
and then
That's that would have been on the multiple choice answer. Had they not given you a nice number like 9, had they given you 8, then the answer would be log base 3 of 8 plus t plus 4.
so what if they did log base 3 of 8 plus log base, or just I guess plus t, and then plus some, instead of 4 it was like log base 3 of, I don't know, 2.
Nothing wrong with
You'd
that
have,
answer as a final answer. If I had something like this, that's a final answer. In other words, other than going to the calculator and finding out the number that is.
but if they're the same
That's a
bases,
number. So you could actually add the numbers, but the problem is that once you go to the calculator and you replace that with a decimal, you've rounded it off. So this, if I had an answer like that, that's the final answer. 4 plus that log plus that log. I would not want to convert those to decimals and round them off. The precise exact answer is this.
but let's say instead of log 2 to 7, it's log 3 7.
Then
You would just,
I can combine those two logs into the log base 3 of 8 times 7, which is 56.
then, so let's say the 4 was log 3 7 and the 2 was log 3 8, like it is, or like we substitute, then it'd just be t plus log 3 56 would be the simplest answer.
Yeah.
Okay. Cool.
Yeah, logs are a little like irrationals. In other words, when you have an answer square root of 2, they don't want you to turn that into 1.41. They want it left as square root of 2. So if I have square root of 2 plus 3, you might think, well, now they want you to turn it into 1.41, so I can turn that into a single number, but they don't. That is the official answer, square root of 2 plus 3. Same thing with logs. You don't turn those into numbers. You can simplify them sometimes, but you don't turn them into numbers. In other words, if I had that as 8 times 7, then I can certainly multiply those together and get 56. But that's all I can do. All right. That's probably a good place to stop. What did we get through? We got through number 8.
Yep.
Yeah. Now, yeah, so I don't know. I guess good luck on your test tomorrow.
Yeah, the only other thing besides like logs on the test is like a equals p to the ERT or whatever, and I already know how to do most of that. You just substitute in.
Well, it feels to me like you understand logs also. I feel like you understand logs better now than I've ever felt like you understood them before.
Yeah.
Okay? But you do have to know those rules. And there's a couple of other nice things just before I go here that's useful to know about logs. Yeah. Okay. One of them you already know. What's the log of 1 equal to?
0.
Yes, no matter the base. That's because b to the 0 power is equal to 1, no matter what b is. So the log of 1 is always 0. The log of b is always 1. So those are two pretty powerful things to know. And b to the log base b of an exponent is whatever that is. In other words, those tend to cancel one another. The answer is whatever that is, whether it be x or x squared. All right, Zach, good luck. And I will talk to you. Let's see, you have another session
Tomorrow.
tomorrow. I thought so. You still need that session? Is that session before the test?
No, it's after.
It's after the test? Do you need that session still? That's fine.
I don't know.
I don't have any problem with it, but are you going to want a session right after the test?
Yeah, let's cancel it, I guess. Yeah.
Okay, I'm not trying to talk you into canceling it, but
it was at 11, correct?
Yes.
Yeah, let's cancel it because I don't know what ROTC is having me do tomorrow. So.
Okay. How do you like an ROTC?
It's a lot of work, but it's fun. So.
Yeah. You're probably working on drills, marching drills, I would think, at about this point. First year, ROTC.
Marching drills, yeah, we did like squad movements, land navigation.
Yeah.
All of that.
I did good at squad movements. I was good at that.
I think they're fun. I like playing them out.
Left flank, march. Yeah, I do too. I always did like it. So, all right, Zach, I will talk to you next time. I think you have some more scheduled next week or something.
Yeah, I scheduled them until the first week of December, I think.
Yeah, I'm glad you mentioned that. Which is fine with me. If that's convenient for you, go ahead and keep doing it like that. If you want to do it, in other words, if you don't want to take the time to go in there and schedule 7 different ones and want to do it during a session online and just tell me, I'm always willing to do that too, if it's easy.
Okay.
In other words,
I tried to
you're
stick
looking
with
at my calendar right now, so you could go through here and see where I have blanks and say, yeah, give me that one, this one, this one, and this one. And I don't know how difficult it is to schedule 9 different ones online. Do you have to fill out your name, email, and phone number each time, or does it remember those?
like on an iPhone, it just automatically puts it in.
Okay. So it's not too terribly difficult to do.
Yeah, iPhone's like after you do it like the first 2 times, it picks up on like repeated behavior. So.
Good. All right. I'll talk to you next time.
All right.
Bye-bye.
Bye.